In this video, I'll be explaining the binary search's time complexity and why it's in the order of log n. If you wanted to know how the binary search works, please refer to the previous video titled Python 78, How the Binary Search Works. We've talked about different searches for that particular program where the array was 11, 12, 13, 14, 15, and we showed the number of comparisons for number 11, which is 2. For 12 is 3 number of comparisons. For 13, this was the best case where only one comparison was needed. And 14, 2 comparisons, and 15, 3 comparisons. So in the best case, if the element we're looking at is sitting in the middle, exactly in the middle, or is actually at the midpoint. So let's talk about in the best case. If the target element is located in the middle of the array, like we can see here, during the first comparison, the binary search completes in just one comparison. Therefore, the best case time complexity is constant, which is order of 1. Now, in the worst case, the binary search requires log base 2 n comparisons to find the target element or determine that it's not in the array. This occurs when the search has to split the array down to one element. So if we saw that when we were searching for 11, we only needed 2 comparisons, whereas when we searched for 12, we needed 3 comparisons. When we searched for number 14, we needed 2. And when we've searched for 15, it's 3 comparisons. And if we're searching for, say, a number that's not in the list, like 16, it also takes 3 comparisons. And that's the worst case for this particular example of an array of 5 elements, where the maximum number of comparisons would be 3. Okay, so it's in the order of log n because the algorithm halves the search range with each step. Each comparison removes half of the remaining elements, so the number of comparisons needed to find or not find the target grows logarithmically as the list size increases. I'm going to show you how that works. So let's just suppose we've got an array, an array of 16 elements. So I'm just going to sort of scroll down and try to visualize this a bit better. So array size, and say here 16, and if we double that, so 32, if we double that, say 64, and if we double that, 128, double 128 is 256, so that should be enough. And let's just put a border around that. So the number of comparisons needed for 16 would be dividing that by 2, so that's 8. Another divide by 2, so that's 4. Another 2, so that's 2. And by divide by 2, so that gives us 1. So the number of comparisons needed is actually 4. So that would be number 4 here. Now for 32, we split that by 2, so that gives us number 16. And then I'm going to copy this range and paste it. So that's a total of 5 comparisons. Now 64, if we divide that by 2, it gives us 32, and then copy again. It's 32 divided by, so it's pretty much the same. So it takes us 6 comparisons to find what we're looking at for an element, an array of 64. So that's the maximum, say. And for 128, divide by 2, so that's 64. Paste 256 divided by 2 is 128. I hope I got these numbers right. If they're not 100% right, just look at it up approximately. So for 256, it takes 8 comparisons. 128, 7, 6, 5, 4 for an array of 16 elements. And so that's pretty much it. I've also got here approximately of 1,000 elements, that's 10 comparisons, and an array of 1 million elements, that's 20 comparisons. We can do this on the calculator, and I'm going to show you how to do that in the next video. Thank you for watching. Stay tuned.